So I'll briefly introduce our moderator, which is Rodney from Keio University SFC campus, and who's going to moderate the discussion. And just a reminder that this is an ongoing series between Keio University Cyber Civilization Research Center and Columbia SIPA. Greg, you want to make a brief comment before we turn it over to Rodney?
No, not at any length. I just thank everybody for continuing the dialogue over time. We've got some new people here, so that's great. I think, we will continue to evolve both the participants in this and, and the subject matter. I'll let Rodney, sort of introduce anybody, but just thanks everybody for joining tonight. And we're relatively rapidly, I'll probably close with a little bit of a preview for the next thing we'd like to do in April. So Rodney, over to you.
Morning or afternoon or evening or wherever you are. So I'm Rod Van Meter. I'm you can call me Rod or Rodney, doesn't matter. And I've now been a professor at Keio's Shonan Fujisawa campus in the Faculty of Environment and Information Studies since 2007. And I've been working on quantum computing since March of 2003. And the reason I can name that fairly specifically is that's the month that I was laid off of Nokia, where I was prior working on 3G networks and things like that. And I switched into working on quantum full time at that point. And it also happens to be the month that my younger daughter was born. So I always know exactly how long I've been working on this. So my background is in classical computing systems prior to working on quantum stuff. I worked on computer architecture and particularly on network storage systems and some on operating systems and things like that. So for me, switching into quantum was kind of a big shift. But when I was an undergrad, I took a class from Richard Feynman at Caltech titled Potentialities and Limitations of Computing Machines. And from that point in time, I've been interested in what sort of the physical limitations on computation actually are. Although most of my career prior to switching into quantum was really straight up classical ordinary computing systems. So, back in 2003, I sort of looked around. I was looking for a big change in my career, that I want to do something that's potentially, that's high risk and potentially very high payoff. I looked at DNA computing and analog computing and a little bit at AI and things like that. And I settled on quantum computing, and now it's 20 years later. And these systems are getting, as you all know from seeing it in the news, they're getting increasingly real every day. And we're reaching the point now where you can run real algorithms on the quantum hardware. Theory and algorithms and hardware and important topics such as error correction all seem to be sort of moving along roughly in lockstep, so that we're making progress on all fronts. But there's still quite a ways to go before these machines are really sort of practical and used day to day to solve interesting problems that people need to solve in sort of a production environment on a day-to-day basis. But we're continuing to get there. So now is really an exciting time to be in the field, and it's really an important time to be having the discussions, because particularly today, a couple of the people we have as speakers today are experts in cybersecurity. And any of you who have worked with any sort of classical computing system, but particularly in the area of security, know that big changes take a long time. And so it's important to have the conversation starting early and figure out what the right time frame is for dealing with things. So I have lots of comments and lots of questions and lots of things we can talk about, but that's probably enough of a introductory set of remarks from me. Alicia, who should we go to next?
We can go in any order. So George or Colin, if any of you have a preference.
Why don't we go to George first? Yeah.
Okay. Hi, everybody. I'm Georgianna Shea, but I go by George. I'm the Chief Technologist at the Foundations for Defense of Democracies. It's a very small think tank in the DC area, although I live in Colorado. I get to work remotely, so I'm very happy about that. I would say FDD is about 45 people, and of those 45 people, there are about 5 that focus on cyber issues. I'm one of those 5, and I'd like to think that we're very impactful. In my current role there, I'm the I guess I run the Transformative Cyber Innovation Lab, TESOL, and my job is to demonstrate technologies so that decision makers, policymakers can better understand them, and to help further cybersecurity. So, one example I usually give people, I got to FDD about 2 years ago. It was right after the SolarWinds compromise. Excuse me. So I started working on SBOMs, software bill of materials, and I can say that 2 years ago, not a lot of people knew what an SBOM was, but now it's become a very, I would say, commonplace term in cybersecurity. Software bill of materials is a list of the component software in software, because usually software is about 90% open source. So I will take a subject and then research it, socialize it, help people understand, so policies can be made, decisions can be made. And more recently, I just did a paper on information theoretic secure, which I think got me to this forum tonight. So thank you for having me. And I was confused at first because I was like, I'm not a quantum expert, although I did write a paper on something with quantum. I stayed at Holiday Inn Select. So my paper on information theoretic secure states of things was looking at the post-quantum computing age coming about, and the effects it's going to have on cybersecurity, and then the actions you can take now to help prevent some of those compromises. I won't get into all of the paper right now, but that's kind of what got me started on this topic. My background, I have, say, over 20 years in cybersecurity. Actually, before it was a word cyber, it was computer network operations. I've done cyber operations, cyber defense, cyber attack, cyber exploitation, cyber policy, cyber issues in law enforcement, cyber test and evaluation, mostly supporting federal space, predominantly the Department of Defense. However, I also have worked projects with the Department of Justice and Department of Energy. And I think I stated I'm not a quantum expert, but knowing that post-quantum algorithms are going to help prevent some of the post-quantum attacks on us later kind of puts me in the space. I've been looking at some of the predictions for quantum, and you find that there's around 3 to 28 years range of experts saying that that's when we're going to have post-quantum quantum computing here that will be able to break modern day encryption. So that's very concerning to me, and it's not so much that I can predict the date. I like to tell people with quantum, it was easier with the Y2K because you had an actual date, the Y2K. But with quantum, again, it's like 3 to 28 years based on the experts. And again, I'm not the expert, but when you look at how cybersecurity has been slowly taking hold in industry and standards are still being developed, implemented, it becomes very concerning. So it's one of those issues that, like the SBOM, I'd like to raise awareness to it right now.
Great, thank you. And our other panelist today is Colin Soutar. Colin?
Thanks, Rodney. So my name is Colin Soutar. I'm a managing director within Deloitte, based in the Washington, D.C. area. And I guess by background, what got me into the field of quantum, happened to have a PhD in physics from many, many years ago. So that's sort of more coincidental than anything else, but allows me to at least track some of the concepts that are used in quantum computing. After that, I did a postdoc at NASA Johnson Space Center, working on using material called photorefractive material to process information. And we were looking at doing autonomous rendezvous and capture of spacecraft at that time. And I went to apply the same techniques to biometric technologies, recognizing individuals, of course. At that point, it was with fingerprints. We also got into iris and face. The reason I bring up that background is I was in a company there for about 14 years and ended up being the CTO for the last decade or so. So really saw an industry like that around an emerging technology evolve through the years. and also the interplay between that technology and standards and regulation. And so I became very interested in what was going on in the quantum realm, let's say about 3 or 4 years ago, and picked up some of the contacts that I'd had in the past with the National Institute of Standards and Technologies. We had helped them develop such emerging technologies, frameworks around privacy, IoT, the NIST cybersecurity framework, and all of those activities were putting particular technologies in the context of risk management, but also with perhaps a half an eye towards what is the potential regulation down the line. Deloitte is 350,000 people worldwide, but even in the US, and even if you look at cyber specifically, which is what I focus on, we have about 3,000 practitioners in the DC area supporting federal applications, or at least supporting government applications, and then another 3,000 on the commercial side or so. So we're very well balanced across both what's happening in the federal domain, where some of the policies are being issued, some of the mandates are being issued, executive orders and the like, but also we're very cognizant of what that means for our commercial counterparts and our clients that are on that side of the house. So we've started to try and craft messaging, which I'd like to talk about further today, around quantum, because it is such a broad topic. And my opinion is a lot of the discussions items get conflated together around the evolution of quantum computers, around the timeline, as George said, about when that's going to impact information. And people really, merge those two together and lose sight of the fact of what you need to do today to manage cyber risk. And we've started putting some of that messaging out. We've been supporting the World Economic Forum for the last 2 years or so as they have stood up their program on quantum cyber readiness. And some of those activities are really with an eye to trying to make sure that there is cogent, concise messaging out there around the quantum threat to cyber, so that people are not either underreacting or overreacting to it, and they're taking prudent steps to calculate that as part of their risk management process. So thank you for giving me the opportunity to be here tonight, and or morning for other people, and I look forward to the discussion.
Good. Let me give just a few more remarks and sort of set the table for some of this, and then we've got sort of a set of potential questions we can talk about, and then after that, then we'll open it up for other people to potentially offer comments or questions. So, I sort of swim in this environment, assuming that people have at least some sort of basic familiarity with quantum computing and quantum technology, but that's actually probably not true for everybody who's listening in to this. So let me make just a couple of introductory remarks here. So I really think of quantum as being essentially the third information paradigm. So, we had analog information, including, going back to the early, to prehistory, and then of course, written systems and various forms of writing, and then ultimately analog recordings like records and wax cylinders and things like that. And then we moved into the digital era, really starting, I guess, in about the 1940s. Depends on sort of how you count and what you consider to be useful technology. And then now we are moving into the just starting to move into the quantum era, and this is the third major information paradigm. Hang on just a second. So, I think of this as really being the biggest change in information processing that's happening, potentially in this century. We'll see what happens. The basic idea is that you take simple quantum effects. You take the effects of single electrons or single photons, and you combine them into groups, and you use two key quantum concepts that are quantum superposition and quantum entanglement. And the idea is that if you use these effects well, you can represent essentially digital states in this, but you can accelerate the process of computation such that rather than iterating through all of the possible solutions to a problem, what you're doing is you're looking for interference patterns. And these interference patterns, if you can use them to drive a quantum algorithm, can solve a class of problems faster than you can with ordinary classical systems. And it's not so much actually that there's a constant factor that's faster. It's that quantum computing systems have the potential to change the scaling away from exponential growth in the complexity of solving a problem as you increase the problem size towards something that's polynomial. The range of problems that can be solved for that is really still being investigated, and our understanding of that continues to change every day. Obviously, since we're talking about cybersecurity, one of the things that generated a lot of the interest was Peter Shor's discovery in the mid-1990s that you can use this technology to factor large numbers, potentially in polynomial time rather than in sub-exponential time, which the best classical systems were known for. But Feynman originally proposed quantum computers for solving problems in quantum chemistry. And so there are also a lot of applications in chemistry and optimization problems and quantum machine learning and a whole variety of things. So I think that's probably enough of a sort of setting to, I think, get us started.